We all know that IP for contribution media is mostly used for long distance. It's when you need to take content between major cities across large distances that we are compressing the content and putting it over IP Ethernet. So what we have seen in recent deployments is that it's also gaining acceptance for relatively high bit rate, actually really high bit rate uncompressed transport. As Ian was talking about, we are actually using 702022-6, and we are transporting uncompressed media across the whole of the UK right now. Actually, at NAB, we actually had a little press release. That was kind of a strange one because BT actually broadcasts 4K using uncompressed video between, I believe, India and the UK. And it was dual paths. That means 12 gigabits per second on a primary and 12 gigs on a secondary path, just to get that really important content over. So what was it? It was a cricket match. So 1 billion viewers, basically. So really, really important stuff. So the drivers for the growth of video over IP, if I may, is really the cost of bandwidth, right? So gigabit Ethernet is relatively cheap right now. We are seeing a lot of video over 10 gigabit Ethernets over DWDM networks in the local metro area. And really, it's all about infrastructure extension. How can I really take my content and share it over a wider area network between multiple studios, for example? And what's really accelerating this is really standardization, right? There's no longer a need for proprietary systems. SMPTE is one of the standards bodies is actually pushing this. So really, the standardization has been a huge help. We also right now have a better understanding of how to take video over IP. It's no longer just launching video into an Ethernet network and hope it gets there. We now understand that what's the required quality of service, what kind of service level agreements they need to put in place, what kind of forwarding mechanisms that needs to be there in order to get your content there properly and completely. So how do we actually increase and accelerate acceptance? So we believe that there's three things that we really should be looking at. Of course, it's to increase reliability. Broadcast content is all about getting your content there in a very secure, very static manner. You know exactly where your media goes and how it actually gets there. So we need to be able to ensure that increased reliability, but also what we would like to do is actually to increase the familiarity. How can we actually transition users from baseband type applications into a baseband over IP or video over IP type application? Excuse me. So an important factor is, of course, to building hybrid networks. And one of the key things that we have done, or we've seen the industry do, is actually hide the IP beneath the user interface. So to the end user, it's no longer a baseband infrastructure or IP infrastructure. To them, it's one user interface, and the infrastructure can really be anything at this point. So what are the three keys are basically resiliency, monitoring, and centralized management, where centralized management would be like an SDN type application here. So in terms of monitoring, what we strongly believe is that we need to apply comprehensive monitoring to target fault finding. Because taking video in a traditional manner, just using a multi-viewer, looking at the output, if the video is lost, you kind of trace it backwards. But it's typically a single stream per connection. With video over Ethernet or IP, suddenly it's literally tens or hundreds of streams. So how do you actually find a fault if you don't correlate all the parameters in the network with a service, for example? So really, really intelligent monitoring is really necessary. With centralized management, what you need to do is provide complete control over system connectivity. What we like to say is that we never use our video over IT, right? So we never use the IT protocols that's in place. Instead, we use video over IP protocols, but we throw away a large number of that dynamic behavior. Instead, what we do is we enforce centralized management to ensure that we build the correct paths to get your packets where you need to. one of the key factors in video over IP is resiliency. So standardization is usually important, of course, and within the SMPTE specifications, there's algorithms and protocols for the transport of video over IP or Ethernet, but there's also protocols for forward error correction. And just 2 or 3 years ago, what we have is the release of RTP switching mechanism that actually provides seamless switching with path diversity. But these standards can actually be extended. So these protection mechanisms can be extended to give you even more protection. So with RTP switching, we can actually provide highly enhanced designs that accepts packets from any stream. So you can think of it as 100% forward error correction, so that you can actually run your broadcast content without any disruption at all. You can think about truly redundant systems with 1+1 hardware redundancy with the RTP switching to assure that there is no disruptions from link faults, network faults, node faults, even complete dropouts of a master control, for example. So what are we talking about? For those that's not familiar with RTP switching is essentially the encapsulation of video over IP and transmitting it over 2 diverse paths. So it's basically a primary and a secondary feed that goes over 2 distinct network paths. And at a receiver, standalone receivers basically select the best packet for regeneration of the signal to give you the perfect switching. So in the case where there's a fault, one path is always active, so your signals are always received without any errors whatsoever. With hardware protection, what we essentially would do is to extend this with dual hardware and essentially send the streams down a primary path and a secondary path down to a slave transmitter. Now, because this is entirely Ethernet, this link between the 2 hardware pieces can live over any Ethernet network. So one of our applications, for example, is actually for radio, where we have a master control and a disaster recovery site that's actually separated by 100 kilometers geographically, right? So this is to ensure that you have the highest level of redundancy possible. So just by leveraging Ethernet and its algorithm and its protocols, we can actually give you or give the end user highly redundant systems. And so this can be extended by doing cascading dual receivers at any of your receive sites. And in the case of a fault, your signals are always transmitted into the network so that you always have continuous media, right? So you're guaranteeing the service across the entire network itself. And on a receiver, of course, the receivers work independently, so they are always receiving content and protecting from each other, like so. Now, so protection is only one element. Media monitoring is also an extremely important element, and it's typically an afterthought, right? So we always invest in the transport of content, all the production facilities, but no one actually puts in a lot of funding into the monitoring systems, right? So when we start putting content into Ethernet networks, that changes completely, right? So you need to be able to track down where a fault occurs within a network. And that could be a switch element, it could be a media adapter, it could be even a faulty stream due to packet losses on a particular link. So monitoring must be approached from a holistic approach. You need to be able to paint a picture of the entire network itself. You can't just expect to monitor the endpoints and hope to diagnose a fault. So there are many standards, that actually guide how you can measure and characterize a network for fault definition. There are standards for video, standards for audio, standards for Ethernet networks, and for network performance. But most importantly is actually the correlation in the monitoring itself. how do you get all these alarm parameters, bring it together, and still be able to figure out where the faults are, right? So one of the key applications for such a scenario is target fault discovery via correlation. So let's say you have a number of links in your network, and this could be just a subset of your entire network. Everything is fine and dandy, everything is green, there's no faults, and suddenly a fault occurs, but where does it actually occur in the network is unknown, right? So what we need is actually a system that's able to trace, for example, where the actual fault starts and ends within the network itself to give you targeted fault recovery. And how you would do that, of course, is to have monitoring capability across all your nodes and elements, to monitor all the equipment and streams that are present. You'll start associating these streams and equipment with connections, with physical connections that's associated with services. So with this information, you can actually start collecting information for QoS, a quality of service, quality experience, so that you can comply and meet service level agreements. And, right? So with this kind of information, you can also look and say, hey, I'm approaching 75% of my bandwidth capacity. Maybe it's time to upgrade and start adding equipment to actually be able to grow the network. So with all the information that you can gather, right, so you need to think, how is it that can I actually present all the information that I can find a fault and resolve that fault as quickly as possible? So our method of doing this is actually a higher level network management system that takes an SDN approach, which we'll talk about later. It extracts all the information in real time and actually correlates all the services through thumbnail views or through services, through service level maps that says whether a service is at fault or not. And you can drill down into the system and say, I know exactly where the fault is, and I'll send my operations staff to actually go fix it or to make changes in the network. So what we feel actually, even you have a highly protected network, you have great monitoring, essentially what's the most important is how you can actually simplify the complex. And here, this is where we talk about a little bit about SDN. If we look at the difference between baseband and IP networks, traditional baseband networks are typically locked down. They're not dynamic. The flip side is that they're highly reassuring, right? So all your content goes everywhere, you know where it goes. It's on a specific coax cable, properly labeled. I know where it's going. If there's a fault, I can trace it down in that manner. Because IP systems are dynamic, with individual elements making decisions for themselves, you don't really know where your packets are going. So it gives you a highly flexible environment, but by definition, it's non-deterministic and insecure. So if you look at a traditional broadcast infrastructure, we have content or sources on the left going through a set of, or a mesh of video routers that's tie-lined together so that you can distribute content throughout your facility. And end users would basically be entering through a UI, going to the controller interface to make connections in the network. So once you selected a source and destination, what the controller would do is actually specify how the signals are routed through that distributed router network, right? So this, by definition, gives you traffic engineering through tie-line management. So how different is it from an SDN-type network with centralized management? Instead of baseband routers in the mesh, you have Ethernet switches. Right? So what you have is media adapters or sources, or camera sources with direct IP outputs that goes into the network. And the users would actually use the same method, go into the controller to make the connections. And what we have is a centralized connection system, management system that actually makes those changes and routes the traffic to where it needs to go. So in this case, you can do unicast or multicast, point to multi-point type transport. So one of the key things in actually achieving such a scenario application is an SDN-like control connection management system. So one of the proposals or one of the things that we've done is actually build deterministic algorithms that allows us to actually say, when an end user says, I want my source to connect to my destination, I look at my entire network, how will I actually route the traffic through the network in a deterministic fashion, right? So once you have a proper algorithm, you can apply such an algorithm to get very, very deterministic routing and switching in your network, right? So obviously the goal here is to get your content where it needs to go in a relatively flexible manner, but in a highly predictable fashion, right? So you let the network, or you let the management system actually route the traffic for you to ensure that your packets get there. So how do we do such a thing? One of the methods that has been used in the past is actually to use VLAN trunking. So I build VLANs for videos as it crosses a mesh of Ethernet switches. One of the problems with such a system is that the way that we configure the systems today is traditional CLI-based command line interface. So we write commands to the switches itself, and the switches will actually parse those configuration changes in a native operating system, but it's very, very slow. So in our test, just pushing multiple VLANs into a switch can take upwards of 4 seconds for the first packet to exit the network. So it's not a very broadcast-like instant-on type scenario. It does, however, provide very deterministic switching, because what we're actually doing is that you're throwing away all the protocols in the network and saying that I'm going to build a path through a network to ensure that the packets go along that path only. Then you have another method which is protocol-based, for example, using IGMP in the plant for multicast transmission. It's actually relatively speedy. The problem is that it's also relatively indeterministic, right? So based on loading and based on how you design the architecture, you may actually have bandwidth loading issues that prevent videos from actually being transported properly. So the goal is to say, okay, all right, I want to be able to build connections and provision services, and no one really wants to go into the system and build and make changes to IP addresses on the fly. So what do we need to do to actually use some of the new systems to increase the familiarity and the use, make it easy to use, right? So on the front end, you can think of it as a UI with input sources and output sources that that the operator defines, that enables all the connections. And in the background, what you have is a controller that actually makes all the connections for you. So the controller in this case is based on software-defined networking. So it's been previously talked about, so I'll skip this. But what I want to talk about is OpenFlow and how OpenFlow actually provides a huge amount of benefits. One of the most important use cases of OpenFlow is actually auto-discovery of nodes and links, right? The issue with Ethernet switches, for example, is that once you put in a network, you don't really know how to configure them on the fly immediately for transmission or for use for transport of videos. But with OpenFlow, insertion of Ethernet switches or connection of new links can actually be automated. You can automatically discover resources on the fly. And once those resources are discovered, you can actually use that capacity immediately for transport. So what it does is provides a highly scalable system that you can start very very small. And as and when you need additional capacity, you start adding additional elements to actually increase your bandwidth. Another unique function of OpenFlow is that it allows any flow in the network to be transported with very little requirement for software drivers. You don't really have to build software drivers for every single media adapter at this point, because what we're actually doing is you are actually managing the switches, and based on MAC addresses or IP addresses, forwarding it from a source to a destination. And this is possible because it uses packet inspection matching modification, right? So I can actually create rules within the system that says that any packets received from this MAC address, if it's within this range, pass it to the next element, and the next element will actually say whether to forward, to modify, to replicate, so on and so forth. So if you look at a leaf and spine architecture with a core of 10 gigabit Ethernet switches with 40 gigabit uplinks, you can actually build a small little network with 4 sites or studios. And you can add capacity very easily just by adding additional Ethernet switches into the network and creating a much larger network. One of the really important benefits of this such a system is actually automatic access control, right? If you imagine, or if you take a look at a network where everything is managed centrally, when an element is not in use, it's automatically disabled. So no one can actually start putting equipment into your system and potentially sending road packets in your network, for example. So, for example, if I have an Ethernet switch and it's under the control of this system, any port that's not in use is automatically disabled. So no user can come in and plug in another system and actually start sending packets or start receiving packets from your network. So this gives you security in your network. And once the network is started running and all the packets are all the media adapters are configured as expected, if someone were to come in through a secondary control system and turn off a port, for example, with centralized management, you can actually go in and enforce the expected behavior so that your content will always be flowing. All right? So it prevents people from making changes on the fly. And with this, with OpenFlow, we can extract a lot of information, and we can start aggregating and correlating. We can get switch information, link and packet performance statistics to build a network map to give you a very good view of the actual performance of your network itself. So very quickly, I'd like to discuss, or rather describe a national broadcast network that exists in the UK today. And so what we have is that the British Telecom built a nationwide contribution network, right? So this is a network that's not bespoke. It's actually a network that can be used by multiple end users, but it was really developed for a specific broadcaster. And what they had is 12 main studios interconnected with 28 remote facilities in a dual star topology for highest possible resiliency. All of the 12 main studios were connected via 10 gigabit Ethernet for uncompressed SDI over IP. So they wanted extremely high quality, extremely low latency. The remote facilities were connected via gigabit Ethernet using JPEG 2000. Again, there were 2 data centers for extremely high resiliency, so that traffic could go, so that traffic would always go through two cores, and everything was centrally managed for both connection and alarm management. So from a network topology perspective, what they have is essentially a dual star with their data centers in the west and east of London. All the critical sites, 12 critical sites, can be anywhere. The only distinguishing factor between the critical sites and the regional sites are the bandwidth, right? So the critical sites are connected via 10 gigabit Ethernet, while the regional sites are via gigabit Ethernet only. And the differentiation here is actually the ability to pay, all right? So the end users that use 10 gigabit Ethernet are the ones that could afford that high capacity bandwidth. If you look at their network, it's very simple, and all they had at the customer premises is a monitoring solution followed by SMT 2022-6 media adapters that converted baseband SD and HD into 10 gigabit Ethernet, which was aggregated by a Juniper top-of-rack switch. So this is essentially a 10 gigabit Ethernet switch that feeds into a DWDM network, going to a dual core at the data centers. So the data centers basically does the reverse, followed by monitoring to ensure that the videos received from the customer prem is transmitted with the identical performance as that as received. So the goal for this network is high resiliency. So what they wanted to do was build a really, really robust network. So every single customer premise would actually be connected into the 2 data centers, but will also be cross-strapped using the 1+1 hardware protection. So what this gave them is that their content will always be received regardless if there's a media adapter failure, a local Ethernet switch failure, a link failure, an entire data center failure. So content will always be received regardless. Now, this originally was designed for the broadcaster, but it's not a bespoke environment. It's actually a multi-tenanted environment. What BT did was that they gave the user access control. So the end user, or in this case, the ITV, they would actually go in and start making or booking connections by themselves, all right? Based on the system design, they requested at least 30 concurrent users making a minimum of 30 bookings a day without any fault in the network. Currently tested to 50 concurrent users, up to 100 bookings a day without any decrease in performance. So the primary features of this network or this particular application is that they wanted media to be shared in real time between any location. Previously, there was at least a 600 millisecond delay. With the uncompressed sites, now they are down to a couple of milliseconds. Centralized management, connection management enables non-specialists, so anyone can make the connections. As long as they have user rights, they can go in and make connections. In the past, connections would require at least 5 minutes. Now it's down to 4 seconds, so it's as near real time as they can expect. And this allows the end user to actually share content in a very dynamic fashion and very cost effectively too. And that's it.
All right then, Chin. Thanks very much for the comprehensive presentation. Anyone, any questions? Come on, I was hoping somebody was going to surprise me with a question and I wasn't going to have to drum up one. All right then. I see that you're always talking about uncompressed sources here. Yes. Are you assuming that all of your uncompressed sources are all going to be less than 10 gig? Or are you sort of thinking about, say, going to 40 gig or 100 gig type interfaces? Are you seeing demand for that?
Not at this point, because a lot of our applications that we see actually uses multiple 10 gigs. Yeah. And with the network configured as it is, you can actually send traffic down any of those 10 gig links, right? So from that control perspective, 40 gigs is still too expensive. So we use multiple 10 gigs to actually do the transport.
So as and when the interface price comes down, you just use straight 10 gig lane technology for doing it. And I mean, unlike all of the other presentations that have talked about 2022-6, you've actually mentioned some of the deeper protocols for synchronizing video in an IP domain. Do you have any plans for doing things like splicing and so forth for local insertion of uncompressed content?
So one of the things that we are actually doing right now is actually RP168 switching, but that's not done at the switch level. That's actually what we call destination timing. What we are actually demonstrating is that you can receive 2 streams, buffer it, and do a RP168 switching at the destination itself. Right. So in a normal production facility, we don't see more than 10% of it as to live. So normal switching would not require it. So it's only for those 2 live sources that we actually do the RP168.
Okay. And when you're in the, say, looking at the overload situation, because I mean, inevitably broadcasters are going to be interested in the fallover situation that you get, where you do actually get contention and breakdown of delivery of real-time traffic. What kind of warning are you going to give to your users that you're approaching that level where you're not going to be able to sustain real-time video?
So based on the current system today, we do have a what we call a theoretical map based on bookings, but we also extract actual utilization because we don't own the networks, so end users may actually start putting data traffic in there that we may not know of. So what we actually do is we do a comparison between what we expect to be there and what's actually being used, and we report that. So our current threshold is 75%. We do now, once we hit 75%, we start reporting that you need to be aware that your next video circuit might actually not go through, and you might have to start taking things down.
Okay, well, it's good to know that the things that Johnny Dolvik tells me, you're actually backing up. But can you all give him a round of applause?